So we are going to discuss the PageRank algorithm in this talk. So today morning I did a Google search to find out how many websites are there on the entire web. And I don't know if what I found is authentic, but one of the first hits to my query said that in January 2012, the estimate is 14 billion. I mean, websites to which you can crawl and reach. And this piece of information is also provided by Google, so I don't know how true or how authentic it is, but okay, you can take it on face value that it's something like that. How much is 14 billion? It's 14 into 10 power 9. That's a large number. It's over 10 power 10. Is that right? Maybe this is pages. You're right. So not this is probably the number of web pages. Okay, and one of the reasons why Google is considered a good search engine is that when you ask a query, you get good sites very quickly. It gives you good answers, the answers that you want. Among the first few things that you're interested in, it gives you the answer that the thing that you are interested in. Although the paper finally, which I zoomed in on to present the PageRank algorithm from, I took quite a while to find this because the others somehow were not to my taste or satisfaction. It's not always the case, but everybody is very happy with Google. And one of the reasons is apparently because of the PageRank algorithm. At least that is what is widely publicized by Google as. That could also be a marketing strategy, that the PageRank algorithm is being what it is. It's the reason why Google is doing so well. So what is the PageRank? What Google does, ranks all the web pages. So it stores this huge vector which assigns a numerical rank to all the web pages. And when there is a query which it processes, and it's a partial retrieval query, there's a number of pages which satisfy the query, that keywords that it's looking for, whatever search it does. It gives you the list of answers according to this page rank, according to the rank vector that it stores. And even though there may be hundreds of hits to the partial query that you make, it turns out that most people are happy with the first few answers, or they zoom in onto what they want pretty quickly. And what you're going to discuss is the algorithm that Google uses to rank all the pages. So this is so basically what it does is what is called importance score vector. Which assigns an importance score to every web page. The importance score is just a non-negative real number. So it's just a number, and the ranking is according to the ranking given by these scores. No, it doesn't depend on the query. I think it doesn't depend on the query. Okay, let's assume that. Let's take it on face value that it doesn't depend on the query. The query is going to give you a list of pages which are the answers to your query, and that is ordered according to the page rank.
Score is also dynamic, right?
Every month apparently it is updated. The page rank is updated.
It may depend on the queries that happen.
The updates might influence the queries, surely. Yeah. So every month there is an algorithm that is run, and we'll try to figure out how long it will take, etc. I haven't actually tried to calculate, but we can try and figure out how many operations it would take to to compute the page rank vector. And there are algorithms which do some kind of recomputation. If you already have a page rank vector and the web has undergone small changes, there are algorithms that can efficiently recompute approximately the new page rank vector, not exactly. Okay. Yeah, in general, there are these three brutal things that Google seems to do. One is to crawl the web and get all pages. And the other is to build database. Okay, that is a very sophisticated thing, I guess, because different keywords, and they have their own importance of keywords, etc., which index into the database. I don't know how the database is actually organized. Some kind of partial retrieval, maybe B-tree-like structure, I don't know, because it's something that's suitable for partial match queries. So they organize this database. And the third is this page rank. Three very huge operations, but then incrementally done, I suppose, as you go along. So what is their idea of ranking pages? It's a very democratic notion of in the following sense, that they don't look at the contents of the pages to figure out whether it's important or not. A page is important if the web considers it important. So what then would be a measure of importance of a page? How many links point to that page? So that is, say, one way of thinking about the importance score. So importance score of page J could be number of links to J. But that could be, isn't that, do you think that is really representative of the entire web? Just counting the number of links that point to page J, would that be representative of the entire web? Because what I can do is to just create a little network of my own with many, many edges pointing to my page, and thereby say that I am a very important page. Okay. So what matters is not just the number of links that point to J, but the importance of those links. How many important links point to J, because that is more likely to be representative of the entire web. Somehow the information that is spread across the web somehow passes on importance to a particular web page. Okay. So this is alone is not enough. So what we want additionally is somehow weight by the importance of the pages pointing to J. So we somehow want to bring in that as well. But notice that there is immediately a circularity in the definition. The importance of a page is defined by the importance of all the pages that are pointing to it. Okay. So both the left and the right hand sides are defined by this unknown quantity which we want to discover, which is the importance. Okay. We'll handle that. And the other thing about democratic, so the way we can think of it here is that it's not quite democratic in that sense, but it's democratic in the sense that you want to be reflective of the entire web. So everybody gets to vote for a page by setting a link to that page. And the weight of your vote depends on your importance. Okay. The other point is that I shouldn't get to have multiple votes. If I shouldn't, if I cast 100 votes, I shouldn't become more important because I have 100 links pointing out as compared to another person who's only one link pointing out. Okay. So my importance is going to get divided up into as many pieces as the number of links that are pointing out from my web page. It's similar in spirit to not allowing a person to vote multiple times. So let's say that xj denotes the importance score. Then what we are talking about is, so let's say n I is number of links going out from page I. And suppose page I points to page J, then the contribution of page I to page J should be xi divided by ni. Okay. So if I points to, I links to J, it contributes xi divided by ni to xj. Okay. So what does that mean? So what is xj then? Xj can be therefore written as the sum of all xi divided by ni, where I belongs to Lj. What is Lj? Lj is set of pages linking to J. So it's a circular definition in the sense that both left and right hand sides depend on this unknown quantity which we want to figure out. But this is the simple idea of, I mean, this is these are the numbers that we want. We have to make sense out of these numbers and see if we can compute them efficiently. So it's convenient to think of it linear algebraically. This is a set of linear equations in these unknowns. So x1, x2, x capital N, where capital N is that huge number. These are the unknowns, and you are looking for a solution to the system of linear equations, right? So obviously you want to write them as a system of linear equations formally. So what are the matrices that are involved? So the system of linear equations is going to look like Ax equals x, because the x vector is on the right hand side. And what is the coefficients vector A? Let's figure out the jth column. Or the ith column, sorry. In this coefficient vector. So the entry xj here is the jth row multiplied by this. And all the things that are going to contribute are those which link to j. So in the ith column, you've got 1 by ni in all the locations, ni many of them, to which I has a link. Okay, so this is a matrix. You can say that A ki is 1 by ni if I links to k and 0. So there is this huge matrix, 14 billion by 14 billion, and the page rank vector that you're interested in is a solution to this system of linear equations. Okay. See, although it's a huge matrix, it's likely to be a very sparse matrix, because typically what is the number of links that go out from a page? I think the average number of links that go out must be not more than 100 or so, or maybe it's even less than that. 100 is probably a very generous number. I didn't try to figure that out. If somebody here knows, you can tell me.
Maybe for a Wikipedia page,
100 links go out from
Wikipedia, and some
certain pages. Okay. So in any case, it's a very sparse matrix. Okay. So it's much smaller than 100, or should be much smaller than 100. Okay.
No, anonymously, let's say they have links to all affiliated colleges, so it's like something like 500 links are going on.
So we are only interested in the average. So on the average, if it's small, the graph is sparse. Some columns, like the Anna University column, may be very dense, but most columns are likely to be sparse, I guess. Okay, so this vector x is also called as an eigenvector for eigenvalue 1. First question is, why should such a vector exist at all? You all know what eigenvalue and eigenvector means, I guess. So lambda, so A is any matrix you say lambda is an eigenvalue and x is an eigenvector for that eigenvalue if Ax equals lambda x. Okay. So in other words, you are looking for solutions to the system of linear equations, and if this is not a full rank matrix, this is a homogeneous system of linear equations, this will have a non-trivial solution. X should be a non-zero vector, of course. you're looking for a non-zero vector which satisfies this, which means x is a solution to this system of linear equations, which means that determinant of A minus lambda I must be 0. It should be a singular matrix, not an invertible matrix. But that means lambda is a solution to this polynomial, which is a degree n polynomial. This is degree n polynomial. So it has n roots, complex numbers usually, it has n roots. How do I know whether 1 is a root of determinant A minus lambda I for that, for this huge matrix which we have just defined? Fortunately, it's something that we can quickly figure out by using the fact that this matrix is column stochastic. Every column adds up to 1. It's like a probability vector. Every column A is column stochastic. That is, each column sum is 1. It's non-negative and it is 1. So you can think of it as a probability distribution on the n web pages in the entire web. Each column vector is like a probability distribution. It has non-zero probabilities not on many nodes, not on many pages, only ni of them, which is small, but it's still a probability distribution. The other point is that this is the same for A or A transpose. It doesn't matter what you, so the eigenvalues of A are the same as the eigenvalues of A transpose. Okay. So in other words, I can also look at Y transpose A equals Y transpose for a row vector Y and ask if this has a solution. If this has a solution, it means that A transpose Y equals Y. So Y is an eigenvector for eigenvalue 1 of A transpose. That would mean that 1 is an eigenvalue of A transpose, and since A and A transpose have the same eigenvalues, 1 would be an eigenvalue of A as well. What is the simple solution to this? If you take the all ones vector, the all ones vector multiplied by each column is going to give you 1, because each column adds up to 1. When you take the inner product of the all ones vector with a column of A, that's just the sum of the entries of the column, and that's going to be 1. So if you say E is the all ones vector, then clearly A equals E transpose. So that means 1 is an eigenvalue. But what we want is a right eigenvector. The page rank vector is the right eigenvector for the eigenvalue 1. Okay. And that's not so easy to find. But we know it must be there. Okay, so is it as simple as this? You have written down the system of equations and you just have to find x. There are a couple of issues that we need to deal with. There are 3 issues, in fact, which we need to deal with. The first one is, what if there is no unique solution? Let's call this star. So if there is more than one solution, you have different conflicting page rank vectors. Which one do you take? How do you resolve that issue? It's a serious problem because it might be the intuition behind the page rank vector somehow was that you would get something that is uniquely defined. We'll see that the reasons why there could be different page rank vectors is quite nasty, and it will mess up with your intuitive notion of an absolute ranking of pages that you would like to have. The second thing is, which is another niggling problem, is that here when I said this, when I said that E transpose A equals E transpose, I've assumed that there is no column which is all zeros. No column of A is all zeros. So when I say that every column is a probability distribution, which is like, all the non-zero entries are 1 by ni, adding up to 1, it is because I'm assuming that there are no nodes which are so-called dangling nodes in the web. There are no pages which have no links going out at all. If there are pages with no links going out, they will correspond to 0 columns. In that case, 1 is not an eigenvalue. So there is no solution to the equation. Okay? So the problem of dangling nodes. So it's an easy exercise to prove that if there are dangling nodes, then 1 is not an eigenvalue. Okay. So if there are these dead ends, like one of the examples that Nari drew when he showed a little Markov chain with 2 states, and there was one dead state. The dead state is like a dangling node in the entire web. Okay. And the third thing is, how do we compute it? Compute X in reasonable time. The nice thing is that all the 3 issues are addressed by one simple solution. All the 3 issues are going to be addressed by one solution. And the solution is a kind of engineering solution which just works. Okay, it's based on some linear algebra, but it's just an engineered solution. The problem of dangling nodes, 1 is not an eigenvalue. So what if there is no unique solution? Can you give me an example of a small web? So by now it's clear that for us, web is just a 14 billion node directed graph. It's just this huge directed graph. Can you give me an example of a small directed graph for which 1 is not an eigenvalue? For which, if we take the corresponding column stochastic matrix A, 1 is not an eigenvalue. So let's take, consider this graph. I'm taking a very simple example. It's a disconnected graph. So what is the matrix A corresponding to this? It's a 6 column matrix. What is column 1? All the things coming out of 1. So that is 0, 1. What is column 2? Three is what is 4? Five. Six will be so you have these 2 blocks. This is this little block which is column stochastic in itself corresponding to this subgraph, and there's this other block which is column stochastic corresponding to this. Of course, the entire thing is also column stochastic. Okay. So what we could do is take a vector which is an eigenvector for eigenvalue 1 and put 0 corresponding to this block here, or the other way around. So can you give me an eigenvector corresponding to this block for eigenvalue 1? What is it? All ones. Okay, but we want to think of it as a probability vector 1 by 3, 1 by 3, 1 by 3. Okay, and you put zeros here. That will give you 1 by 3, 1 by 3, 1 by 3, and zeros here. Or you could put these 1 by 3 blocks here and the other way around. Okay. So you have two linearly independent eigenvectors corresponding to the eigenvalue 1. One in which you put 1 by 3 on top and zeros below, and the other one in which you put 1 by 3 below and zeros above. So the page rank vector is thought of as a kind of probability vector only. So then it's a non-negative vector, and so you can assume that you're going to scale it down, divide all the entries by the sum of the xi's, so that the whole thing adds up to 1, and that's why I put 1 by 3 and zeros there. So if you have a setup like this, then there is no unique solution. It turns out that if the underlying undirected graph is connected, then there will be a unique solution. No, that's also not true. If the underlying undirected graph is connected, if there are strongly connected components sitting at, dangling at two leaves, the stuff that Nari described, then you can construct linearly independent vectors for those, if you have something like this, let's say, and you put a strongly connected component here, and you put a strongly connected component here, then you can construct eigenvectors which are linearly independent, one corresponding to this, one corresponding to this. Put only non-zero weight on this, and then you will have an eigenvector which corresponds to this for this graph. You can check that out easily. Another one which corresponds to this. So if the graph is not strongly connected, then there can be multiple solutions to this. Okay. So how are you going to ensure that this huge graph it's not going to be strongly connected? We know that this huge graph consists of very small strongly connected components. People link to each other basically. And otherwise it's only loosely connected, the entire web. And there are many dangling nodes. Apparently 80% of the pages on the web are dangling pages. So how do we deal with this?
Why can't we put just one node and just put all the nodes, a link from this node to all nodes? Like it's huge, but one solution.
That's the solution. So from the dangling pages, you are going to put a uniform link to all the pages. That's how Google handles it. So from each dangling node, put an edge to all the pages. Or Google assumes that there's going to be, that means you are going to, if you get to a dangling node, so okay. So let me give you another picture of how Google is going to find this vector x. Much of the thing, so you're not going to solve a system of linear equations. Even after I know that there is a unique solution to this x, I'm not going to try and use Gaussian elimination to solve the system of linear equations, because that is very expensive. It's cubic in the dimension of this, and we have already seen that the dimension of this is huge. It's like 10 power 10. So you can't use Gaussian elimination to solve this. Okay, can't solve the system of linear equations. Instead, what Google does is what the algorithm does is it's a method called the power method. But for that we need to set up things a little bit. It's going to iteratively find x. It's going to start at some arbitrary probability distribution, say the current page rank vector, and then A is modified. A has become a new graph now. You're going to apply A iteratively to this current, to an arbitrary page rank vector, and that will converge once things are set up correctly to the correct eigenvector. And it will rapidly converge once things are set up correctly. Okay, so in other words, what does it mean to apply A to X? It means that I'm going to start at a node that I pick with the same probability distribution as defined by X. X is basically a probability distribution, and I'm picking a page according to that probability distribution. And then applying A means that I follow the out edges with uniform probability. If I'm sitting at a page I with ni edges going out, then with probability 1 by ni, I go to any one of them. I do a random surfing, basically. That's what applying A once means. If I apply A k times, it means that I'm taking k random steps. I'm a random surfer and I'm taking k random steps in the graph. If I hit a dangling node, I'm going to do a teleportation, or that's what Google does. They call it teleportation, which basically means what you said. With probability 1 by capital N, jump to any page and continue the random walk. Okay, so does that make sense? It turns out that this intuition matches with the original intuition of saying that, so when you do a random walk for sufficient amount of time, the probability with which you will be at a page will roughly correspond to its importance score. Okay, you can prove that formally. But we need to deal with these situations first. What if there is no unique solution? That's because there is more than one strongly connected component. So here is an example. I leave it to you as an easy exercise to work out that you can define, you can see that this has linearly independent eigenvectors for eigenvalue 1. One which is supported here and 0 here, and conversely.
What I was suggesting was to take care of this thing also, because you said that if the graph is strongly connected, then it will have a unique solution, right? So instead of from dangling nodes you put a link outwards, you make one node, a new node, which is adjacent to, which has incoming and outgoing edges from all the nodes.
And
Takes care of both. Like now there will be no dangling nodes also, and the graph will be strong. And that one page can be rendered like this.
it will just assume that there is that page, you mean?
Yeah, they create that page. So,
See, if there are going to be, so how many edges are going to be incident on that page?
all.
Yeah, I think that will okay, so I think that will disturb the page rank a little too much. So let's just go to the solution that Google offers, or the page rank algorithm offers. So what you're going to do is, you're going to choose a kind of, what is it called? It's some parameter. That parameter has a name which okay, I'm not able to find it. So this is going to be it's a parameter, and what you're going to do is just take alpha times A plus 1 minus alpha times the following matrix: 1 by capital N E transpose. So let's consider the following matrix. Instead of the matrix A, we are going to replace it by this matrix. Alpha is a number between 0 and 1. Okay? Alpha is going to be a large number. So you want to give a lot of weightage to the original matrix A, which is the actual web. And what is this matrix? E into E transpose is the all ones matrix. E is a column vector consisting of all ones. E transpose is a row vector. So it's the all ones matrix, the J matrix. and you're putting 1 by capital N everywhere. That means it's a uniform probability distribution matrix. It is the complete directed graph with self loops. You're going to use that with probability 1 minus alpha. See, alpha is going to be large. The value of alpha that Google chooses is 0.85 apparently. So you give 85% weightage to A and only 15% weightage to this. I think the effect of what you're suggesting may be a little too lopsided. Okay, so this takes care of the strong connectivity problem because this is a complete graph. It just comes and sits on top of it, but with small weightage. Now you have weighted edges. With small weightage, it comes and sits on top. It takes care of the graph, the underlying directed graph being strongly connected, and the important thing that Nari mentioned in his talk about the underlying Markov chain. Because there are these self loops, the Markov chain becomes aperiodic. It's irreducible, as it's called in the Markov chain literature, which is the same thing as strongly connected, and therefore the random walk converges to the stationary distribution. So if you start with the probability distribution X and apply A repeatedly, it will go to the unique eigenvector corresponding to eigenvalue 1. So that takes care of this problem as well as this problem. Okay. Not quite, because this problem is the matrix itself is not stochastic. All the columns don't add up to 1. So even after I do this, all the columns won't add up to 1. So what I must do is, first I'll transform A to another matrix A prime, which is just A plus the matrix where I put 1 by n in all the columns which correspond to dangling nodes. So I'll call that 1 by capital N D multiplied by E transpose, where D is basically the vector which is zeros and ones. I have 1 if this is a dangling node. So in the ith location, I'll have 1 if I is a dangling node. And zeros otherwise. So in other words, this is a matrix which has got 1 by n in all those columns which correspond to the dangling nodes, and you're adding that to A because you have zeros there. Then this becomes A prime becomes a column stochastic matrix, and you use A prime here. Then what you get is M is an actual stochastic matrix. It behaves like a Markov chain properly, and this is taken care of and this is taken care of. So the theorem, let me just write down the theorem that we are using from Markov chain theory in order to do this. So if M is a Markov chain that is strongly connected, one strong component, okay, and aperiodic, then starting at any probability distribution, M converges to the unique stationary distribution, which is the eigenvector for eigenvalue 1. So in other words, you can start at x0 and define xk to be m of xk minus 1. And what we know is xk converges to x, where x is a solution to mx equals x. And how rapidly xk converges to x is going to tell you what the running time of the page rank update algorithm is, the page rank algorithm. And that interestingly is governed by this parameter alpha. So if you make alpha smaller, you will not be faithful to the original structure of the web. You will be jumping around at random too often, but you will converge faster. If you make alpha too large, then the algorithm will run too slowly. So 0.85 is what they've arrived at as the right number. So here, strongly connected, we know what it means. Aperiodic, simply read self loops. You have some weight self loops at every node. Okay, these two things take care of the behavior of this. Okay, let me show you a couple of small things here. How do we know that? So let me try and prove one or two little things here. Yeah, what are the things that we need to argue? One is, how quickly does this converge to X? That's one thing that I need to tell you. The other is about the fact that if it is strongly connected, then there is a unique eigenvector corresponding to eigenvalue 1. And then I think these are the two things. Okay, let's just. What does it mean to say that M is strongly connected? M is actually a matrix which is column stochastic. And if you give me any two nodes I and j, I can find a path from I to j such that all the edges on the path have non-zero entries corresponding to it. I can also find a path from j to I. Okay. For any pair of nodes, I can find a directed path from one to the other. So how do I prove that it has a unique eigenvector corresponding to eigenvalue 1? Firstly, okay, first thing I would like to argue is that every eigenvector corresponding to eigenvalue 1 is either going to have all entries positive or all entries negative. Okay. So suppose not. So suppose, so claim 1. Oh, I'm going very slowly. How much more time can I take? 10-15 minutes? I don't think I should be proving these things in detail. Every eigenvector for M corresponding to eigenvalue 1 has all positive or all negative entries. Why is that true? Suppose it's not true. Since it's a strongly connected thing, there will be a pair of nodes I and j such that, so these are the values. So mx equals x, and x has both positive and negative entries. So there will be a pair of values such that xi is say positive and xj is negative with an edge between them. There are positive and negative, so there will be two adjacent guys with edge in some direction, an edge between them. Now let's look at the equation corresponding to, so summation m kl, the kth row, ith row, mik xk is equal to xi. So here for us it means the other way, no? The columns are the adjacencies going out of I. Okay. So I know that Mij is non-zero. So summation Mik xk is equal to xi. Take absolute values on both sides. So this summation is both non-zero, so has negative entries. Xi is positive and this has negative entries in it. Okay. So all of them can't be negative. If all of them were negative, xi would have been negative. So there are negative as well as positive non-zero entries in it, which means when I take absolute value of xi is absolute value of summation Mik xk, that is strictly less than summation, the summation is over k, Mik absolute value of xk. Okay. So for this I know for at least one I this happens. Absolute value of xi is strictly less than summation Mik absolute value of xk over k. Now add this up over all the i's. So when I do summation absolute value of xi over all the i's, all the others will be less than or equal to maybe, but this one is strictly less than. So when I take the summation, I can interchange it, summation over I Mik absolute value of xk. But this is 1. These are the column sums of this column stochastic matrix. So I've got a contradiction because summation of absolute value of xi's is strictly less than the same quantity. So that means either all the entries of x are positive, of course I can take minus of it, then all the entries are negative. Now what you can easily check is if you give me two linearly independent guys, suppose x and y are two linearly independent vectors which correspond to the all ones vector, I can choose a linear combination which will also be an eigenvector for the eigenvalue 1, which has some positive and some negative. I can choose a linear combination whose sum adds up to 0, for instance. I leave that to you as an easy exercise. You can find alpha and beta such that alpha plus beta, alpha x plus beta y has both positive and negative entries. Just by choosing alpha, sum adds up to 0. The sum of all the entries adds up to 0. There's this index that is running over. No? So if the sum adds up to 0, it's a non-zero vector, there must be some positive, some negative in it. And we have just proved that it's not possible. Therefore, there must be a unique eigenvector corresponding to eigenvalue 1 when it's strongly connected. So that's something that I wanted to argue for you. And the other thing is this magic parameter alpha. How does it govern the speed of the rate of convergence? Let me just tell you that in 2 minutes, and then a few more remarks and I'll wind up. So what are the see how does the algorithm work? You start with an arbitrary probability distribution and keep repeatedly applying m to it. Every time you apply m, so if you take a probability distribution, you can check that m into x k is also a probability distribution because it's a convex combination of probability distributions. Each column is a probability distribution. So it's a convex combination, therefore that's also a probability distribution. You'll always get a probability distribution. So let's say you start with x0 and at some point of time you start at x0 and let's say q is the eigenvector or x is the eigenvector. The eigenvector is also a probability distribution for us. What can I say about x0 minus x? Let's call this vector v. What can I say about this vector v? Notice that summation vi is 0. The sum of all the entries of v is 0 because this adds up to 1 and this adds up to 1. So the difference is a vector whose entries add up to 0. So I'm interested in vectors of this form whose entries add up to 0. Let's see what happens when you apply m to such a vector. What happens when you apply m to it? M is defined right there. It's alpha A prime V plus 1 minus alpha by n E transpose V. What is E transpose V? E transpose is the all ones row. When you take its inner product with this vector V, it's going to give you the sum of the Vi's. So this just goes to 0. So MV is just alpha times A prime V. Okay. The other easy thing to see is that the L1 norm of A prime V is at most the L1 norm of. So what is the L1 norm? What I mean is just the sum of the absolute values of the entries. Okay. So the L1 norm of, I'm going to measure how quickly this converges by trying to figure out how quickly the L1 norm shrinks. I'm going to find out how rapidly the L1 norm shrinks. Okay. Sorry? A prime? A prime V won't be equal to AV because A prime, I've added those, I've made it a column stochastic matrix. A is substochastic because it has dangling nodes. Now A prime is a column stochastic matrix. It need not be strongly connected. So because it's column stochastic, you can easily argue that this will be bounded by this. Okay, I'll leave again that as a simple exercise in triangle inequality basically to check that this is upper bounded by this. Sum of the absolute values of the entries. I just had to use the fact that the columns of A prime add up to 1 and that's it. Okay, so because this happens, what can I say about norm of alpha A prime V? It's at most alpha times norm of V1. So every time I apply M, the vector which is the discrepancy is shrinking by a factor of alpha, and alpha is like 0.85. So if I have a tolerance parameter epsilon, I just need to apply, I'm converging exponentially rapidly, which is defined by that 0.85 which is there. Okay. Yeah, so this is how you, basically this iterative method is called the power method for finding the eigenvector, and it converges rapidly because alpha is a constant that's bounded away from 1. In L1 norm it converges rapidly. There's just one final thing. How do I do this matrix? I still have to do a matrix multiplied by a vector computation. Normally a matrix multiplied by a vector takes quadratic time, right? Every row of M into this, that will take linear time. Quadratic is bad here because 14 billion square is very bad. Fortunately, I mean this is a sparse matrix. So they just use the standard textbook sparse matrix trick. You write down the matrix as a bunch of triples, a list of triples, row index, column index, value. And when you want to do M into X, you just run through the entire thing, accumulating the sum appropriately. You are looking at Ij, you know where it should go, that sum should be updated. So one pass over this bunch of triples accumulates that. And the iteration takes whatever, that's governed by alpha to the power whatever, you know. That's the error parameter. Yeah, I guess they use many machines to do this because it will take many man hours of computation. Even if you say it is linear in 14 billion, and how many operations can you perform in a second? How many arithmetic operations in current machines? 10 power 7. Billion. 10 power 9. Arithmetic operation, multiplications. They are slow, no? Yeah, the other important thing is they, since the number of nodes is 14 billion, that's like whatever 1.4 into 10 power 10. In the probability vector, they want to calculate the denominators with 12 bits of precision, 12 decimal, not bits, 12 decimal places of precision. Whereas only then they have a clear page ranking. And so that's also going to be, so it's multiple precision arithmetic. So I didn't try to calculate how many days of, or what is the total number of, computer hours you'll need in order to do this. So this is the impression that I have. So the stuff I'm describing is from this article by, mostly from.
There are some techniques for optimizing the search engine ranking. So what they do?
See, there's only one thing that I've read, that there's this. So what do you mean by optimizing the ranking? There are a couple of interesting things that I read. One is that instead of using E transpose here, so there are these, so it's like you say that page rank is important and it becomes a kind of self-fulfilling prophecy sort of thing. Everyone wants to have high page rank. And there are people, spammers, who create these link farms which provide lots of links to push up your page rank and so on. So to beat all that, apparently if you change this the second vector here, so this is the rank 1 matrix. Instead of using E transpose here, they use what they call a personalization vector, which tries to push out the influence of these link farms, these spammers who try to influence page rank in different ways. And that is, but that's not optimization of the running time. So what do you mean by optimization here? Is it the speed at which you compute the page rank vector, or give better page ranks? I don't know. So then it must be based on some other semantic information of the pages, not just, so here what we have done is just the structure of the graph, not the contents of the pages at all. If you use only the structure of the graph, I don't know what else they could use. Yeah, the other thing, apparently there's a lot of research in trying to, in figuring out efficient ways of doing this updation. See, you have a page rank vector. In a month's time, maybe several thousand new nodes will be added, many links will change. So you can assume that a small fraction of the graph has changed. Is it possible to update the eigenvector without having to do this entire computation all over again? And there are some interesting suggestions. What you do apparently is, if you assume that only a small number of nodes have changed, you can collapse the rest of the web to a single node, work on the small graph, and kind of paste it onto the original page rank vector. And that gives a good approximation to the correct page rank. This is a paper by somebody called Chien and the two Kumars, Ravi Kumar, Shiva Kumar, and one more guy whose name I don't remember. It's a few years ago. So that's one thing that I noticed while Google searching. So this article is quite nice. It's by Brian and Liza. It's called the 25 into 10 to power 9 dollar eigenvector problem. Eigenvector, the linear algebra behind Google. No, apparently things like this, eigenvalue problems physicists have dealt with over, ages, and such techniques are standard apparently in trying to solve compute eigenvalues for huge matrices. They work with these lattice gauges or stuff like that, which they again deal with large matrices and solving eigenvalues. These techniques are not really that new apparently.
In the analysis, it was crucial that there was an E transpose there in the analysis.
Yeah, so I don't know when you replace E transpose by this personalization vector, how the linear algebra works. I haven't tried to figure that out. that struck me as well. Yeah, the fact that these error vectors are in this subspace of vectors which add up to 0, and they get killed there, that's crucial. That makes this analysis very simple. I'll stop.